Recording.
Yeah, have a job.
So, all right. So, thanks everybody for being here. So today is going to be the last one, the last lecture. So I'm going to have to be a little selective on which of the remaining topics I'm going to cover it, or which one I'm going to cover to which degree of details. There's still a few things to talk about, but so I'm gonna skip some details and then skip one bit of the story, but I'll tell you roughly what it is about, so that if you want to read it in the paper, I mean, the slides are available on my website, so you can also get them from there. So anyway, let me try to finish with this picture that I was discussing last time, where you put together how you make these various choices of possible different choices of planar structure on trees, and where you assign the kind of metric information of how you embed your trees inside some semantic space that has some kind of metric property. And so I was saying that, okay, the keeping track of the different possible choices of planar structure and how far they are from one another is done by this combinatorial object that is called the associaedron. And the metric data are also compatible with the associaedron. And the associaedron doesn't take into account another kind of symmetry that you have, which is the permutations of the labels at the leaves. And that is instead taken care of by this other side that has to do with just assigning the mapping to semantic space and not the planar structure, which are these modular spaces of the metric structure of abstract non-planar trees, where you take into account how the different trees just as non-planar trees. So a lot of the difference now goes into the different relabeling of the leaves. There's also different topologies, not in this example with three, because that's too small. But basically there are 2n-3 double factorial abstract binary rooted trees on n given leaves. And they have n-2 internal edges. So you have n-2 real variables that tell you how long these edges can be. And this corresponds to this picture of embedding into your model semantic space that I was talking about last time. So you have this other space like this. And one can kind of normalize how you assign these lengths, for example, by saying that they add up to 1 or something, and then you get this a geometric picture that tells you what one says the link of the origin here. So the origin, the middle point is where this tree degenerates, where the internal edges are now length 0. And then you go one way or the other to get the different possibilities. If you look at, you take a small neighborhood of this degenerate point, and you look at how it intersects in space. In this case of three leaves, is just 3 points. Okay, so it's a simple space. But in the case of 4 leaves, it is this graph. This called the Peterson graph is the link of the origin. So you can think of each edge of this graph as being one of the possible different abstract trees on the same set of leaves. So if you have one different possibility as abstract tree for each of the edges in this graph, and the length of the edge is your choices of putting lengths on the edges of this, how to put lengths on the edges of this tree in the way that they are normalized by summing up to 1. So this is a way of thinking of this parameterizing space for all the possible abstract tree with these assignments of lengths that come from an embedding into a semantic space. And the relation between these two, this I'm going to skip all details about it, but I just want to tell you, there's a known relation between these two spaces, the associaedra and these other spaces for the abstract trees. the way that this is done is to say that, each association has a fixed ordering of the leaves of the leaves. And then you look at all the possible different bracketing. So it's giving you all the possible planar trees that give you the same linear ordering of the words of your sentence. Okay. So these are all the possible parsings by planar trees of a given sentence with a fixed order. And on the other hand, in the non-planar trees, you have your unordered set, and you're looking at all the possible trees in the unordered, in the non-planar sense, with the corresponding metrics. And this thing fit together, as you permute the labels, you get a different association. All these different associations are glued together in a geometric object, which is known as to be this moduli space of real curves that the mathematicians have been studying for a long time. In fact, it's called its orientation double cover for topological reasons. And basically comes from looking at these lengths that you're assigning as some lengths in the line that separate points, and looking at these configuration points in the line as an equivalent problem. And that's a way of describing the geometry. So as to make an example, right, just look at the case of with four leaves. The association is a pentagon, and when you start to permute the possible leaves, you get a lot of different pentagons, and these are all glued together according to that picture over there. And you have two of this because of this orientation double cover, and they collapse together in a single form, a single geometric form, which is this great dodecahedron shape. So that's your space for the case of four leaves. And that parameterizes both the choices. Also, a point on this space is what if I pick a point on this space somewhere, what it's giving me. So this point is giving me a particular choice of planar structure on my abstract tree, and B, a particular choice of lengths embedded into the semantic space. So picking a point is take care of both things at the same time. And so you can view, like, if you pick different points, how far they are from each other, how many phases of you have to cross to go from one to the other, and that tells you like how structurally they are. These different choices can be related to one another, how different they are. They give you a quantitative way of measuring, comparing them, and saying how different or similar they are. Okay. This is the role of these spaces. And there is the map when you forget about the planar structure. We have a projection, which is our usual projection from planar tree down to non-planar tree that forgets the planar structure. And the way it behaves on these objects, where with all these pentagon glued together, is that it folds together all of these squares that these pentagons decompose into, which are the ones where you're just looking at the different metrics on a fixed planar structure. And folding all of them together means that all these different planar structures are identified together, and so you lose the information about the planar structure. So the point of this is that these maps are all very explicitly described in geometric terms. And the key identity is this combinatorial identity in the middle. You have n factorial, which are all the permutation of the leaves of a tree with n leaves. That's all the permutation of the leaves. You have a Catalan number, which is the number of all possible planar trees with n leaves. So these are all the possible choices of planar structure when you are allowed to also permute the labels of the leaves. So the left-hand side is what you are parameterizing in this bigger space. The right-hand side, the n to n minus 3 double factorial, is the number of non-planar trees on a given set of n leaves, and labeled leaves. And this remaining 2 to the n minus 1 is how much ambiguity you have in this projection. So it's how many things you are identifying together when you project down from the left to the right. And they are exactly these foldings that you are doing. You have 2 to the n minus 1 things that are going together when you fold these curves or these cubes together. So the point of this is that this is a convenient, geometric thing. Of course, when n gets larger, so n equals 4, we have this pentagon, is like this two-dimensional picture. When n is large, it becomes, a higher dimensional, polytopes, which are, of course, not as easily visualizable. But the thing is that these geometries are extremely well understood from a combinatorial point of view. So there's a very good way to say very explicitly how you compare all these different choices of on the externalization side of the planar structure and on the mapping to semantic space of the metric data. Okay, so this is all I wanted to say about how you compare these different things. So here is a simple example, right? You take something that has a structure like this. You think of it as a planar tree. So you're picking one particular vertex of this associahedron, which is this pentagon in this case. On the other hand, if you think of the underlying syntactic object, which is the non-planar tree, this structure of the non-planar tree is one of 15 possibilities for n equal 4. And you're choosing one particular, so that choice of one of these 15 structures chooses one particular edge in this graph. So you are somewhere there on this edge. And then, you look at your semantic relations between when you map into semantic space, the lexical items that you have at the leads, you look at their relations, you look how closely they are related, you get two coordinates. And these two coordinates give you the coordinates on a certain square, and that square is exactly what relates the two sides of the picture. So you are somewhere on that square. One point on the square is what takes into account both these semantic similarities, semantic relatedness measures on the one hand, and your choice of planar structure, and the other hand simultaneously. Okay, so this is the model combines. So what I mean by saying that this picture combines the two channels of externalization and of assignment of semantic of points in some metric space of semantic relation. All right, so of course, when you have this picture, you can compare different externalizations for different languages because they lead you to different points, and you can say how far they are or how near they are, and other such things, or other kind of algorithm of linearization. You can compare them in the same way. And this, in principle, gives you a potential way of studying question around syntactic parameters. There's those syntactic parameters that have to do with word order relations. I'm going to skip giving any more discussion of this, about the general question of the geometry of syntactic parameters and so on. Okay, so now there's another part in our paper which I'm going to skip, but I'm going to tell you what it is about, so that you can decide whether you're interested in looking at it or not. So it comes from a question. The question is, there is this well-known, long-established relation between grammars and semi-rings, which goes back to Jean-Baptiste Berger in the early 1960s. And since then, it's been developed, and there's a way to organize certain kind of parsings of derivations. And usually it works well for parsing of grammars that are context-free, derivations in context-free grammars, or very mildly context-sensitive cases like joining grammars. So the main setting, you have some kind of deduction rules, and you assign to these values in some semi-ring, you combine them with semi-ring operations, and you obtain values for the deduced outputs of these derivations. So you have a way of checking your derivation work with respect to evaluation in some semi-ring. And so the question that we looked at is how can you extend something like this semi-ring parsing to a case where instead of these context-free grammar derivations, you have merged derivations. And you have characters of algebras as your evaluations in semi-rings. Okay. And the answer to this is simply that yes, you can do that. I mean, you can use the same formalism that I was describing with these characters of algebras and Rotabach's algebra and Birkhoff factorization to obtain an extension of this form of semi-ring parsing to the case of merged derivations. The problem is that this is kind of a long, rather technical story of how to do this. And, I'm gonna skip it entirely because otherwise it would take me the entire rest of this lecture. But the main thing is that, because you're not, one of the things about the context-free is you don't have to worry about where you're applying a certain, that's the key about being context-free. You don't have to worry where you're applying a certain operation, a certain derivation. But in this case, when you compose merge derivation, you go from one workspace to a different workspace, and then again to a different one, because merge produces for you a new workspace. So when you want to compose, composition only works when the target of the first operation is the source of the next one. And so this is changing something which is like composition in a group, where you can multiply any two elements arbitrarily, with what mathematicians call composition in a groupoid, which means that you are composing arrows, and it only works if the first one lands where the second one starts. And because of this fact, which is a very obvious fact, but you have to bring in a lot of formalism that extends these off algebras to something that's called off algebroids, where you exactly have to follow these compositions of arrows that's constrained by source and target having to match. And the same thing for the old package, the Rotabaster algebras and the Birkhoff factorization. Everything has to be modified to follow the fact that arrows have to compose target to source and not arbitrarily. Okay, so I'm just gonna tell you that this all can be done, and this all works. So you get a semi-ring-oid parsing of algebroids and so on. So it's okay. So I'm gonna skip entirely how you do that, and you can, if you think this is a topic of interest, you can look it up. In all the gruesome details in our paper. So I'm gonna just jump through all of this entirely. Let me talk a little bit more about some semantic aspects instead of this. So I'm gonna look a little bit at a particular way of thinking about the relation between semantics and the merge operation, which is because compositional semantic, which is kind of designed to have something that works closely, that has a close relation to the generative process of merge. So the way that formulates this is that on the side of syntax, you have your generative process given by merge. And on the side of semantics, you have another operation that kind of, in a sense, mimics the structure of merge. And it's referred to as combine, and it's formulated, in the Postgres formulation, it's a combination of two things. There's a concatenation operation, and there is a labeling operation. The labeling operation is like keeping track of a head, and the concatenation operation is, in a sense, like merge. Of course, there are two ways that you can think of this. Like if you think of merge as being, as in the old minimalism acting on the planar trees, then now you can think of concatenation as really being the concatenation of the leaves of these trees and the concatenation of the strings. But if you want to adapt it to being the free symmetric merge, then this concatenation should really be itself like a symmetric form, like a kind of like a merge. Okay, but it's still, the result is non-symmetric, at least because anyway you have to keep track of this labeling by a head. So that already we're starting to do some symmetry, even if we try to mimic the symmetric merge. And so the thing that seems a little bit I don't know, not entirely satisfactory with this is the fact that you're sort of postulating the existence of two operations that mirror each other across the two sides of the syntax semantic interface, merge on one side and this combine on the other side. And it seems like you require, why should you have both? Why can't you just use merge to determine the other one, right? And so what one argue is that indeed you can do that. You don't need to postulate separately the existence of this other, merge type operation on the side of semantics. You just use merge. And this is the point that I was making last time, that when we consider this definition of characters of algebras, you're not requiring that you transfer the entire algebraic structure on the other side. The coproduct of algebra structure is entirely staying on the side of syntax. You don't require that the same structure is also existing on the side of semantics. On the side of semantics, you just assume some minimal amount of structure, and for example, I said is this Baxter type projection operation, and you don't carry over. So that means that you just use merge to determine this kind of operation. So let's say that, like last time, we try to extend our mapping of lexical items to some kind of metric model of semantic space, to some function that extends at least those syntactic objects that have a well-defined head. And then, if you do that, then your position in semantic space of a merge of two syntactic objects that has a well-defined head is going to some point that, like I was saying, is some point along the geodesic arc between the two, moving from the head. And then you can say that, okay, my combine is now the image inside semantic space of this merge. So merge is happening on the side of syntax, and I'm just tracking where it goes, and that's my combine. Yes.
Is the idea that in the semantic space, you have this operation of combine, and is the complaint that the result of combining two elements is such that if I look at that result, I can retrieve what two things were combined together? Is that the issue?
So I'm saying that if you use the way that you combine them with merge to know where to map them. So your combine is you combine them with merge on the side, and then you map, and the way you map is coming from the way where you were mapping the two substructures individually, together with some information on semantic proximity, similarity between these substructures.
But Piotrowski doesn't have this proximity or similarity at all, right? Like that.
No, exactly, because that's it. He's not, because he is kind of postulating the fact that you have this other operation that semantic space has a binary operation of combine built into its structure.
So let me just concentrate. The thing is, the reason that I'm asking is that I'm trying to identify whether what you're saying about Piotrowski's system applies to other semantic systems.
Yeah.
That's what.
Right.
Suppose our semantic space is the class of all sets.
Mm-hmm.
It's just all sets. You put them there. That's your semantic space. Of course, there's operations that you can perform on sets, right? Because you can intersect them, for example. So suppose combine is intersect. For any two sets, I just return the intersection of those two sets. It's just as a toy example. Would that also fall in the same criticism as what you're describing?
Well,
that's what
I don't know. So you have to kind of see if you can make a map from merge to that will give you that effect when you map where the merge goes.
You can imagine that like a tree,
right,
with two daughters, is mapped to the set that is the result of
no,
intersection.
to some extent, yes. So let me give you an example of something that I think looks like what you have in mind. Okay, let me give you an example of that. So let me make two comments here, right? For example, for what I'm saying here, the second comment is exactly, I think what you were asking. So let me make two comments here. So because I'm saying now, okay, you don't postulate that this combine exists on its own on the side of semantic, you just take your merge and map it over, and that is your combine. Now, there's some things that maybe one can get worried about, like One of them is, let me make two examples of things that the others, but let me make two examples of things that you might worry about. One is the fact that sometimes you might want to have idempotent structures, and another is whether you can do proper inference or not. And this is like this end intersection type of question that you have. So you say that having idempotence is not a problem per se, in the sense that, of course, on the syntactic side, you don't, right? Because on the syntactic side, anytime you know, so this is, the free magma, so you don't have any relation beside the conductivity, so you never have that any of these objects is either one of these, because this would be a relation in the magma. This is the three, so you never have any relation like this. So in particular, on the side of syntax, you never have any idempotent structure. But on the side of semantics, sometimes you might want to have idempotent structure. This is not an issue in the sense that, when you're mapping this over, so I was saying last time that you can do mappings in which this is going to give you an embedding of the tree inside your semantic space. But of course, this map could also be bigger, so that in some cases it might not be an embedding. Like, for example, what I was saying is that this goes like this. You have the 2 points for these two structures. You have some kind of geodesic arc between them, and you will say that this one is the head of this whole thing. And so you're moving away from the head up to somewhere, and how much you're moving depends on these proximity relations from the head of one and the head of two. Okay, on semantic proximity. But let's say that this could actually is not something just between 0 and 1, but could actually be exactly 0 or exactly 1. And those would be exactly the cases that give you some idempotent structure in the semantic space that's not there in the syntactic, on the syntactic side. So it's not a problem that you can sometimes realize idempotent structures even if you don't have them on the side of syntax. So this is not a problem. And the other question is maybe what you were asking is, how do I do things like intersections and things like this, right? With this idea.
If I just kind of sorry, this
Yeah.
that's kind of what I want to, but kind of just to I want to clarify what's the criticism of Piotrowski.
Yeah.
And one thing that kind of in my head I can identify as a problem is to say that, here's the problem. If you look at the semantic space that Piotrowski defines for us, what's going to happen is that if I give you a certain meaning, you just look at, it's a thing, it's an object. If you look at that object, to some extent, you can guess what was the syntactic structure, what kind of a syntactic structure gave us that meaning. Like if you look at the object, it kind of includes some information, there are certain, it's kind of parsed in a particular way that basically captures some syntactic information.
Yeah.
In some sense or another. That's one thing. As opposed to a system in which if I give you a meaning, if I just give you the object, there is no way, the semantic space can be very rich in structure. But if I give you one particular object as the meaning, there is no way you can guess how that, what sort of thing, what sort of syntactic object that meaning could belong to. It could be a lexical item, it could be a huge tree,
Yeah.
It could be like a million different, basically there is no way you go from meaning to tree.
Yeah.
Is that the point of tension here?
No, so you are right, that in the setting that I'm describing, you could be in the second situation that you described, because, okay, I am inside some semantic space that to me is not very rigidly structured, it just has these proximity relations, and I am at some point here. But, I suppose that now I just know that I am at some point here. So if I'm building where I am, then I'm following like which structure I'm putting together. But if I tell you that I am just here, you could say, well, I am here because I'm coming this way. Or I don't know, I am here because I'm coming, to some other path that's going to some other points. Of course, if this S is very high dimensional, it's unlikely that two paths were going to cross, but it could still happen, right? So you could still be in a situation where you know at which point you are, but you don't necessarily know that you have to be there because of one particular path that you've been following. Yeah.
And what's the problem with Piotrowski is the fact that if you know where you are in the semantic space, you can to some extent guess how you got there.
Mhm.
Is that the?
Yeah, so this
criticism
doesn't
that
force,
there is-
this
that is-
doesn't force that in principle. Of course, if this space is very small, yeah, you might have everything determined once you know where you are, just because there aren't so that many possibilities, right? But, you know, it's just not necessary that that happens. Okay. And so the other thing is this thing about inference, right? Of course, for example, you want to say something like this. I suppose you take these two sentences, John ate a sandwich in the basement and John ate a sandwich at noon. Of course, we all know that this don't imply that John ate a sandwich in the basement at noon, okay? And this is a matter of intersections on that. And of course, the way that you see this picture here is that, you know, of course, suppose you follow what the geodesic arcs are that you use to put these semantic points together. You find that, you know, the one that will correspond to this last point is in the intersection of two neighborhoods of the other points in this metric structure. So you will see that, okay, this is the end implication, which is the Boolean intersection. And of course, it doesn't imply the two separate. So it kind of carries sort of the correct type of inference from the point of view of Boolean operation, just by keeping track of neighborhoods in this metric structure and how they overlap, how the neighborhoods overlap. Okay. So now there's another issue. Now we get towards this type of things like theta relations and so on. So so you wanna keep track of the fact that, you know, when you form, so far, you know, when I talked about the structure of the syntactic objects, I've only looked at the combinatorial structure. So this free generative process of merge. And I've only, on top of that, I've only discussed what happens if you try to impose that these have a well-defined head, and some of them do, and some of them don't. So, but there's more than that you want to keep track of, because you also have the fact that, you know, when you combine, when you build these structures, you also have, you know, I mean, external merge also does, you know, the kind of theta roles assignments and things like this. So you want to be taking care of that. So in some sense, one way to think of how these things will fit is to think that these abstract binary rooted trees that we have looked at only as you know, these abstract binary rooted trees with lexical items at the leaves. But you can also think of binary rooted trees as some kind of functions that take inputs at the leaves. So where your leaves are just legs where you can stick in an input and it produces you an output, which is the entire structure you get, but you can think of that as the output that the roots produces. And so you can think of these you know, hierarchical structures as being formed by this type of operations that take input and give you outputs. And in mathematics, this way that one describes this is to the fact that this magma of this free commutative non-dissociative magma that generates the syntactic object is related very closely to another mathematical structure that is called an operad. And in particular, something related to that is called an algebra over an operad or an operad action. So there's the claim is this that I want to make is that there is such a thing, which I'm going to tell you in a moment what it is, an operad action on syntactic objects that takes syntactic objects as inputs and produces a new syntactic object as output. And one way to describe the compositional properties on semantics is to say that there is an operad action on the semantic space of the same operad, and that these two operad actions that you have on syntax and on semantics are related, which is kind of like saying what I'm saying here, that you define this combined operation by mapping merge, but in a more structured way, making the same claim in a more structured way. And so let me say what these objects are. So an operad of sets, I mean, in mathematics it can be in various categories, but to say an operad of sets is a collection of sets, and in which the elements of each of these sets you think of them as being n-ary operations, so operations that have n inputs and one output. So each of these set is a collection of functions, if you want, with n inputs and one output. Okay. And these have compositions, and the compositions are kind of obvious. You know, you have something that has n input and one output, and you can plug this output into the input of one of the inputs of something else. And so you can plug in all of this, you know, in all a certain number of outputs into each of the inputs and get a corresponding, you know, value. So if I have something that has n inputs and one output, and I have n things, each of which has whatever inputs it has, I can plug all the outputs of these n things into the n inputs of the first one and get something that has a bunch of remaining inputs, which are the ones of all the ones whose outputs I have saturated with the inputs of the next one. And what requires that these compositions satisfy an associativity relation. Let me show that with the diagram, so it's a little bit easier to see what I'm talking about. So here I have something like this. So I have a bunch of operations on the top. All of them have one output. Each of them has a certain number of inputs. And then I have other operations, like two operations. Each one takes some of the outputs above as inputs and take its own outputs to the inputs of the next one. Okay, so I can compose the first thing. I can plug in the outputs of the first row into the inputs of the second row, and then compose the next thing. Or I can do it the other way around. I can compose the second row with the third one, and then plug in the other ones. And the associativity is just that if I do these two things, you know, in whichever order they are the same. So that's the associativity property. And there may or may not be a symmetric structure, meaning that if I permute the inputs and then I permute the next level or vice versa, that I get the same thing. And you know, there are two ways in which I can do that. So there are two possible, you know, symmetry properties with respect to permutations. Not all operands have symmetric. Some of them are, and some are not. So, but the key property is this associativity property. And another set, you know, is an algebra over an operand if it can serve as inputs. So, you know, you have this composition within the operand, but anything that you can plug in into one of these operations as input, and it gives you another object of the same kind as output, is, well, an algebra over this operand, or is something, or you can also say something that the operand acts on. So it's simply like, I'm simply saying these elements of this operand are operations, and I'm telling you what they are operations on. What is it that they transform into something else? So that's the notion of what an algebra over an operand is, and there's a compatibility with this associativity relation, which is the compositionality structure of an algebra over an operand. Okay, so why am I saying this? Okay, let's think about all the binary rooted trees, not non-planar. But now where I don't put anything attached to the leaves. So the leaves are just inputs. I don't saturate them with lexical items. I just let the leaves be with nothing attached to them. Now I can think of these as being an operand with respect to the same merge operation that I'm using to construct the syntactic objects. It's the same magma, but no, now it's not on it's like this core magma that I described, the one when I talked about the Diamond-Schwinger equation, where I don't care about the leaves, the labels. I don't care about labels of the leaves. I just look at these trees and how I merge them together to form all these structures. So the end set of this operand is all the planar binary rooted trees, all the non-planar binary rooted trees with no labels at the leaves. And I think of them as taking n inputs if it has n leaves and giving me one output. And now I can see why this acts on syntactic objects, because if I give you one of these operations, And I give you n syntactic objects. These are themselves trees of some depth, whatever, with some number of leaves decorated by lexical items, but each one of them has a root. And I can append the roots to these dangling leaves of my operation. And this gives me a new syntactic object. So for example, where I have something like this as my operation. And then I have, I don't know, something like this with and then something like this, and something like this. Okay, these are three syntactic objects. I can plug them in. This is my operand action, and I'm getting the new syntactic object. So I have this was no, this thing was an element in my operand with three inputs, and it's taking this collection of three objects. So it's in this SO3, so three product of W. I'm plugging them in, and I get something which is again a syntactic object. Okay. So I'm thinking of this as being operations. And so in a sense, this is kind of like you have this, show this line, you can saturate it with some structure, which is like this predicate in some sense, okay? And okay, let me just keep the pedantic mathematician about how you should really think about the case of abstract trees and ordering of leaves. It's just some small details. And one thing that you can do is also assume that you have a kind of head on this, so that you have decided, no, that you have a head function on this. And then if your inputs have a head function, you will get again something that has a head function. So you can make this compatible with only taking care of those structures that admit a head function. And now you can say that a compositional structure on your semantic space is just something where you can have also an action of the same operand on your semantic space. I'm sort of doing a little trick like I did with this semi-ring last time of saying if something is not parsable, I want some kind of trash bin where I can throw it away. So I add some pointed infinity, which just means my structure is not parsable, I throw it away. And if it is parsable, it goes somewhere in my semantic space. And the point is that I want to say that if I know where my inputs are in semantic space, and as the corresponding images of this structure, I can plug them into one of these operations and get another point in my semantic space. This may or may not be possible. This goes back to the question you were saying, how much I can say where the structure are coming from or once I am already in semantic space. So on the side of syntax, I always have this structure. And you can make your semantics more or less compositional by saying how much of this structure you can carry over on the side of semantics, determined by the one that you have on syntax. And that gives you different scenarios with respect to exactly to the question that you were asking. And right, so you can say that semantic space is compositional if you have a compatible action of the same operand on the side of syntax and that transfers over on the side of semantics. So let's see in what sense this kind of relates to also to these issues about theta theory, theta roles. So when we generate these syntactic objects using external merge, so I don't worry here about the action of merge on workspaces because internal merge is not assigning theta roles. Theta roles are entirely coming, theta roles are entirely coming to the external merge. So I only have to worry about the external merge part if I want to account for something like theta theory. And so this I want to do at some point because as I said, so far I only worried about head function, but you also need not just what the head does, but you also need how the complement of the head is structured in terms of dependence and in terms of theta roles, assignments of theta roles. Something gives a theta role, something takes a theta role, right? And so how do I fit something like that into the picture? I have various types of the various, possible lists of theta roles, of arguments, of predicates, something, agents, locative, whatever, so something. And I want to make sure that, whether in my structure, these things can be assigned consistently or not, when I keep assembling my structures. And so one way to do this is, again, something that is used in mathematics. It's called the color opera. So it's the same thing as these things, but I don't think I have any color, maybe. There it is.
Yeah, I don't.
I don't think these are gonna, these are not erasable. Okay. Yeah, all right, but doesn't matter. So let's say that, you have the possibility of assigning, I don't know, different colors, right? To these legs that you have in your operations of the opera. And then now you're allowed to make the compositions only when these colors match. And you're not allowed to make them when they don't match. And a colored opera is exactly taking a modification of this notion of opera, where you have to keep track that you can only match things if they match. So for example, this would be a composition that you cannot do because your colors don't match, but that in this other order would be a composition that you can do because the colors match. And so you can, take your merged opera and decorate it with the theta roles, and then only require that you have some compositions happen when you have consistency of assignments and not mismatch. Okay, so this is a way to incorporate in this picture this type of additional structure that you want to have at some point. And okay, all right. Let me see. Okay, let me very quickly discuss one more thing. When I discussed internal merge, I said that you don't have to worry about keeping track of the difference between repetitions and copies, because everything you have that, any objects in syntactic objects in your workspace that are isomorphic are repetitions. They're not identical copies. And so you can treat them just as repetition. John likes John, it's not the same John. And so they just happen to be isomorphic things, but not identified. But when you do internal merge, you produce an actual copy, but the way that we will put together the internal merge operation, this copy appears and you take it from one side of you produce the two sides of the coproduct, one with the copy and one with what will become the cancellation of the deeper copy after you apply the internal merge. And so you don't have to worry about distinguishing the copy from the repetitions, because it never lands in the same place. Once everything goes back into your workspace, it's already being, the deeper copy has already been canceled, and what you're left with you no longer have to keep track of what is actually. But there are some other situations where you might have to keep track of the fact that certain things are copies rather than repetition. So I'm taking one example that is discussed in non-spoken merge and the strong minimalist thesis, which is the example of building this sentence. And I tried to read the book, and you try to build it in terms of these objects. And of course, where the two, in this case, the two occurrences of the man are an actual copy. They are the same. They're not a repetition. Okay. So you need something in this situation that actually treats these two as copies rather than as repetition. So it's like saying that you have, instead of where other smaller trees are hanging, but some of these are actually identified, not just isomorphic, but actually identified. Okay. And the way to do this is just to say, so first of all, you want something that does this in a consistent way. So I'm not spelling it out here, but what I just said about the theta roles and so on, you want that you can do this identification only when those things don't violate, different roles. So this structure should not, have incompatible roles. But assuming that this is okay, what you're doing when you are identifying two elements, you're just taking a diagonal inside your space where these elements are really forced to be the same, not just accidentally as more. And then, see, because they're forced to be the same, when you take this coproduct, your coproduct is behaving slightly differently from what I said in general, because these identified pieces, you either take them out all at once as one thing, or you don't take any of them. So they no longer move independently. They no longer can happen to be in some term of the coproduct, but not some of them, but not others. Like they have to they're all identified, so they all move. One of them drags all the others around, and it only occurs once as your extracted term. And so you end up when you do it for this particular example, for example, you end up with the fact that these two demands can only move simultaneously, and so when you extract one of them, you're actually extracting both of them and canceling the different copy at the same time, and they don't move separately. And so you end up with forming the exact thing that you want. So then you have to kind of accommodate, so you can accommodate these other type of structures, and this also is related to something else, which is form set. Is discussed in some other recent papers. None that kind of had the same kind of behavior. Okay, so here let me see. Okay, so now so this is pretty much what a lot of what I wanted to tell you. Sorry for being going a little bit faster than in the previous lecture, but there's one last topic that I want to talk about, and and this is the reason why I have insisted on illustrating as examples these kind of simple-minded and not very clever models of semantics based on vector spaces and these semantic similarities and these mapping over with metrics on the side of semantics. Because of course, nowadays we're all faced with one particular example of things that deal with semantic similarities of this type, which are these large language models that everybody's talking about these days. Okay, so there's been some kind of very dubious, highly dubious, and rather vacuous statements about the fact that these large language models are incompatible or disprove or whatever generative linguistics, which is total bullshit. And in fact, I want to argue that it's quite the opposite, in the sense that the reason why these things work is precisely because you have an image of syntax embedded inside semantics, and that's what they are seeing. Okay, so let's try to see what is happening in this stuff from the perspective that I have been describing. So let's again assume that we have a certain given map that of lexical items. Well, it would rather be tokens in this case. There's a difference between these two concepts, but let me not be too careful about this. So let me say that we have a map from our set of lexical items to some semantic space. And this semantic space we can assume is one of these vector space models that they use, where you look at co-occurrences over some large corpus and semantic similarity on the basis of that. Okay. And now we're going to look at what these attention models of the transformer architecture of large language models do, and how they fit with this idea that I've been describing of algebraic characters and factorization and so on. So before we all seen this picture over and over again, in this time, and this is the way that these transformers architectures are built that one finds in use in all these various large language models that are being used now. There's a lot of stuff that's going on here, but I'm only interested in one thing, which is this self-attention part over there. And I claim that that's where linguistics is.
The where? Sorry, you were pointing and I wasn't sure what you were pointing. You said only
Self-attention.
the self-attention. sorry.
Yeah. So I'm claiming that's where these large language models have anything to do with linguistics. It's in there. And So what is happening in there? So let's say that what is happening there is that one constructs three linear transformations. So the whole entire mathematics that's going on in this business is three matrices. It's not not sophisticated mathematics. So there's three linear transformations. One is called queries, one is called keys, and one is called values. So you start with your given vector space, semantic vector space, and these Q's and keys are mapping it to, say, to other vector spaces. And which are also themselves vector space, semantics in general, of different dimensions, not just what we will understand. So what do they do? So this kind of encode in a statistical way over this, whatever super large corpus of text. Other words that are, so what they're identifying is other words that are structurally related to a given cohort or the structurally related here is sort of phrased in a way that say they are either called by or calling for, but it turns out that it's structurally related really means structurally related in the sense that we want, and I'll say that in a moment. And I want to make a small pedantic, mathematical observation that your vector spaces identify with your RM once you fix a basis. This is a kind of very stupid point, but it's not a very stupid point in the sense that when you write a linear transformation as a matrix because you have chosen a basis, you have in particular choosing a certain order in which you write the rows and columns of this matrix. This order is totally irrelevant because your linear transformation itself is completely independent of this order. You simply want to write it as a matrix, and so to do that, you are choosing an order. And the reason why this observation is not irrelevant is because we are coming from this picture that our generative process of syntax is not based on ordering. And here when I first say, no, I'm taking my list of lexical items as a phrase with its given ordering. But the point is that this is really not relevant. It really is only depending on the unordered set. Okay. But okay, in these various target spaces, you have assumed that you have an inner product that you use to estimate your semantic similarity. So what first construction with query vectors can be thought of as so in my first example that I described of these characters or algebraic characters and so on, I made this example where I said you're mapping to some vector space model of semantic, and you choose some probes there. So you choose some vectors that you want to compare your vectors with, to check if it has agreement or not, and I can change my probe and check how much agreement there is with one or another hypothesis. This is what this query vector is doing. So it is some kind of set, because it's a matrix, so it's a bunch of rows. Each of them is a semantic probe in the sense that I described before. And you can evaluate this probe on your semantic vector coming from one of your lexical items. Okay. And in the keys are a way to turn your lexical item into a set of probes that you can apply to something else. So either your semantic is the subject of being probed by something, or it generates probes that you can test on something else. And this is why they're called queries and keys. It plays this dual role of being probed or probing something else. Okay. And now, the last thing, this values vector, that's simply something that allows you to lower the dimension of these ambient semantic vector space or semantic relations that you're looking at. So you map your items, your semantic vectors down maybe to some projection of something. So that's what the values do. And as I said, you don't worry so much about linear ordering. Of course, it first looks like this because So the way that these query and keys and these parameters are set through learning is that you train your machine for some task. And typically, if one looks at these things like ChatGPT and so on, the task that they use is like the next word. And that, of course, you're imposing a linear ordering. But there are also these bidirectional architectures that are better suited for thinking in terms of the interface with syntax, because these don't look at the linear ordering. You can train them by like masking certain words in a sentence and reconstructing those, and then it doesn't matter. It's not, you don't care about the linear ordering anymore. So that's, you don't really have to impose a linear ordering. People do it because they want certain particular tasks that are defined in terms of a linear order. And so, okay, then you have these queries and keys. So what do you do with them? Well, you pair them. So now you're looking at the proximity in your semantic space of your vectors being, probed and probing something else. And so what it means is that you can take two of the lexical items in your set and see, how much, they are related to each other by the pairing of the queries of one and the keys of the other. What one calls for, what the other one gives. So you see the similarity with theta roles, right? Theta roles, there's something that gives and then something that takes. And here you're kind of probing for something like that. You're searching for something like that, for this kind of structural relations within your tree. The tree is nowhere to be seen so far, but you're searching for it. You're searching for it through trying to guess this give and take relation between some of the leaves of your tree. And you put these measures of relatedness together as a probability distribution, and you weight your vectors, these values representation with these probabilities. And so you weight the ones that have more of these structural relations. When you weight less, the ones that have less. Okay. So this is what these things are doing. Okay. There's another thing that, of course, in this architecture, you usually use a lot of these different attention modules because you need to do a lot of parallel computing. I can't know why you need to do a lot of parallel computing. So you want to be able to do that. They call heads each one of these things, which is a horrible choice of terminology, given that heads for linguistic means a different thing. So I'm going to just drop this multi-attention stuff, because in order just to understand what conceptually these things are doing, we can only look at one of them, a single one of them. Right, so okay, we have our items. We have these three linear transformations that produce queries, keys, and values. We pair the queries and keys to form this probability distribution, and we weight the value vectors by this probability distribution. This is what we're doing. Okay, so how does this fit with the picture that I was discussing in this last couple of lectures? Well, these actually give you this construction that I just described, gives you another example of what I call one of these algebra characters. So if I am actually starting on the side of syntax, I give you a tree, and I can, let's say that it's a tree that admits a well-defined syntactic head. And I can look at this construction, and I can look at this probability distribution of attention from that head to all the other leaves. And I can ask where it's maximized. Okay. And this is my value of my character. So because these are numbers between 0 and 1, this is a character from the algebra to our Viterbi semi-ring of probability parsing. Okay. So I have constructed a character like this of my algebra. So I want to claim that I can use this character to probe, how much these large language models, to these attention modules, are seeing syntactic structures. Okay, let's do it this way. So let's say define what we're looking for. Let's say that we're looking for certain kind of syntactic relation. So the syntactic relation, I think of it as some relation between, so I have my syntactic object, my tree, and I look at two of the leaves, and I want to say if they are in a certain, syntactic relation or not. For example, my syntactic relation can be certain theta roles. Is one of them giving and the other one taking a certain theta roles? Or it can be something else like that. It can be certain kind of structural relation in the tree, or some C-command relation, something. So we list a certain number of syntactic properties that we want to try to see whether they are seen or not by this large language model. So we can say that one of these syntactic relations is exactly detectable by one of these attention models. If when you evaluate it on what this character selects, the argmax of this character, then it is exactly in that relation. So maximize this attention maximizes the relation that you want. Yes.
I'm a little confused by this part, and I was when Bob sent me the paper too. I don't know why there's any need to compare transformers with this formula, because in transformers, there's no syntax, there's no semantics, there's just a bunch of geometric transformations and a next word prediction task. There's no structure, there's no.
I'm claiming that there is.
But
I'm claiming that there is. That's the claim.
the claim is what?
That there is the structure that is built in there, and that it is that these weights that the attention module construct contain the information about the syntactic structures.
Sure, okay, that's emergent though, but the point is that I don't think it gives them too much credit to even bother to try to compare them with.
Why do we not want to bother to try to compare?
Because it's a difference between a linear interpolation scheme, or in this case, a nonlinear interpolation scheme, and what Noam and you and Bob are doing, which is a highly structured model-based scheme. Those two things are entirely different, right?
They are related, they are interfaced. That's exactly what I wanna see here, is how they are interfaced with one another. I mean, these texts that these things are trained on, they are produced by human languages. So they are produced by a mechanism that functions in this way.
Of course.
So somewhere, this thing is in there. You're trying to build an enormous machine that reconstructs an inverse, solves an inverse problem of trying to rebuild, because it has to have eventually, if it has to produce syntactically correct sentences, it has to operate this computational mechanism of syntax. And this computational mechanism of syntax is inversely reconstructed from the image of syntax inside semantics, inside the semantics relations. So it is a solver of an inverse problem. And I want to see how this solver.
Would you call a lookup table a solver of an inverse problem? Would you call a lookup table a solver of an inverse problem?
A what?
A lookup table. In other words, it trains on what? The entire internet, hundreds and hundreds of.
A lookup table is produced in some form.
It's produced in some form, but if it's produced in a form that's so different from this, I don't understand what the benefit is. I'm concerned that the elegance of this theory is undermined by trying to compare it with something that works on an entirely different principle.
If these two things are interfaced, where is the problem that there is an entirely different principle? I'm saying that you're not transforming, all this business, your math from syntax to semantics is not transferring the same structures from syntax to semantics. It's just using the structure of syntax in producing an embedding of syntax inside semantics. I'm not saying that you are going to reproduce the same structure on the side of semantics. That's not my claim. Okay. So what I want to say is that you look for how these structures are realized inside this data, right? This thing that you're constructing. And more typically, you don't expect to see these exactly realizable things, but you expect to see something which is approximately detectable, where you over some sufficiently large data set, you see this relation approximately realized, And this is exactly what happens, for example, in this paper of Manning from a couple of years ago, that showed that you can reconstruct the syntactic trees from these data exactly by realizing that type of approximately detectable relation that I wrote over there. And so of course, here when I say realizable, I mean realizable within a certain context, within a certain corpus, within a certain data set. So let's look in this sense at so if we phrase this thing as a character of algebra in the sense that I'm doing, what does that give us? So I'll say this is a character with values in this Viterbi semi-ring of probabilistic parsing. So we can apply this threshold type Roth-Baxter structure there. And if you do that, this gives you this recursive formula for these characters, this vocally work preparation formula for this character. And what is this seeing for you? So there's a small observation that your head function, when you contract the tree is a tree in your quotient. So here we are taking the quotient where you keep the trace, because in semantic parsing you need to keep the trace of the substructure that you extract. And so you have a certain inequality of how these probabilities work. And because of that, you get the following thing, that when you do this Birkhoff factorization of this character, what it gives for you is a way of tracking where your attention concentrates over substructures. So you get two properties out of that, which are the two properties that I'm listing here. And so the first property that along all these chains, you identify chains of substructures where along all the terms of this chain, the attention remains above a certain threshold, which you can vary, to stratify the picture. And so this first condition is telling you that the maximal attention from the head of each substructure remains sufficiently large. The second condition is simply telling you that when you go down to the nested substructures and you try to maximize the attention at each step, you don't spoil the maximization that you've done at the previous steps. So you maintain this chain of maximization compatible with all substructures. And this is telling you, it's a way of measuring to what extent these probabilities constructed by these attention modules are seeing substructures and their structural relations. And this is a priori not targeted to one specific syntactic relation. You can make it targeted to probing one specific, to what extent you can detect that across substructure consistently one specific syntactic relation by introducing the syntactic relation itself as a Boolean part of your character together with the attention. So these two things are coupled. This is again something that has been done by people by various experiments at this point. And it gives you, the specifically chains where you maximize where your attention, maximal attention explicitly identifies a particular type of syntactic structure. So it gives you a way to see to what extent that these two things are coupled, to what extent, and in what way the syntactic structures are embedded inside these results, these probabilities created by the attention model. So so in this sense we can use this technique of characters and to look at these attention modules as a form of syntax semantic interface. And so what is happening there, if we see them in this slide, you have this very large corpora text, which are produced by human language, so they contain embedded in their semantic relatedness some image of the generative process of syntax to its interface with semantics. These computational architectures, they are sort of these keys and queries are statistical proxies for the syntactic relationship. For things like data theories, command, and so on, for structural relations. And so these things see syntax through this kind of probabilistic smear of how it gets mapped inside all the semantic relations in this large corpus of text. And so the very large parallel computing that is involved is partly because you are trying to solve an inverse problem, which computes computationally hard by construction. And so it's not surprising that you do see the syntactic trees, right? For those papers that is shown. Yes.
There's a question in the chat.
Yeah. So, yeah, there's some questions.
Me? Are you calling on me?
Yeah, I can hear you. Yeah.
I can't hear you, sorry.
Yeah, I can hear you.
The audio's gone.
Oh, okay, I'm sorry. We can hear you.
I can't hear you. Well, okay, I'll talk, but I'm not sure I can hear the reply. Something suddenly happened to the audio. So the question is coming from somebody who doesn't have the expertise to understand most of the presentation, but I think I get a general picture. I'm just wondering, did we need your particular view of the syntax semantics interface and how semantics works in order to end up on this slide, right? So at a very high level of not very thoughtful generality, one imagines that in a language like English, words that are close to each other or adjacent to each other will have some syntactic connection, often via merge, though not always, of course. And any theory that has compositionality related to merge as some kind of principle of semantics, will also have the consequence that there'll be some kind of statistical, higher than baseline probability that where you have one of these words, you'll have the other one near it. So I'm just wondering, whether, I've been to a great extent benefiting from and enjoying the classes that I've been to, but did we need all of these hours to reach this slide?
Yeah, so no, this is a good point in the sense that, what I'm trying to argue here is exactly that, one would like to disentangle a few things, right? Of course, you can say, if I take syntactic constructions that are sufficiently simple, my linear proximity relations are gonna be highly correlated to my syntactic structural relations. But of course, we all know that you can construct examples where they're manifestly not. And there are nice databases of syntactic constructions that precisely highlight the cases where this is not the case. And you can use those as a testing ground for seeing to what extent these type of more sophisticated syntactic structures where there's not an obvious correlation going on, are going to be detectable by these, and to what extent. I mean, what you can expect is that, in general, when you have this type of inverse problem type, you will get an imperfect reconstruction. And there are indications that when you test the behavior, the performance is like on trees, syntactic trees that are more sophisticated syntactic constructions where you don't have agreement between structural relations and order relations. They perform less well than on more obvious ones. And the point that I'm making is that you would like to have a systematic way of testing this. So what I'm arguing for here, is using this, so you're saying why do I want to use this formalism that I've been describing?
Although that wasn't quite my question. I mean, my question was, did we need to use this formalism to get to this slide? I see you may have lots of other reasons for doing what you've been doing, but on this particular point, are there things that are special to what you've been showing us without which we couldn't reach this slide?
So I can tell you this, you need this formalism to get to this slide that I'm showing right now, which is saying that if you want to be able to extract in a consistent way to what extent the structures and syntactic structures and substructures are encoded for cases that are not, too simple, are encoded in this data, then you can use this formalism to do this. So that's where, this formalism. Now for these kind of final considerations that I'm doing here, these are sort of slightly more general type of considerations. What I need this formalism for is the argument of how you go about discussing these properties rather than the question of the assertion itself. And so let me finish this story, with a metaphor. Okay, as you know, I'm started out my life as a theoretical physicist and working for a long time between mathematics and theoretical physics. There is a situation in theoretical physics which is very similar to what we see in this situation now of syntactic theory and large language models. And that is what happens in particle physics. So you all really heard, the news, not particularly recent, but the last major discovery in particle physics was the discovery of the Higgs boson already some years ago at this point. So what does it mean that you discover a particle in particle physics? Well, you have two things. You have quantum field theory and you have particle accelerators. So what it means that I'm searching for the Higgs boson, it means that I'm a quantum field theorist and I'm computing for you a certain generative process of Feynman diagrams, which has its own Hopf algebra structure, its own character, which is giving me the renormalization of this stuff. And I tell you, there are certain particular of these generative processes that are exactly what can happen that will correspond to the existence of a Higgs particle. Okay, so this is where all this computational stuff and all this structure are residing. And on the other hand, you have an enormous particle accelerator that produces an enormous set of data coming from collisions of particle events produced in collisions of particles. You have petabytes of data inside which there's an enormous probabilistic noise. And out of this, through data analysis, and you try to identify a signal. And now, what you want to do with that is solve an enormously computationally complex inverse problem that we're trying to tell me if that signal is this Feynman diagram or that Feynman diagram. Okay, and this is exactly what is happening here. And you have the generative process of syntax is embedded in the large language models in a conceptually similar way. Its image is scattered in a kind of big probabilistic smear of data across a very large number of weights and vectors in a similar way in which my Higgs event, the computed by quantum field theory, is scattered in a similar probabilistic way through this data of a particle smashing event in the Large Hadron Collider. So, there are signals of linguistic structures that are detectable against this background of probabilistic noise. And in the large language model do not invalidate generative syntax in exactly the same way in which particle accelerators do not invalidate quantum field theory. In fact, they prove quantum field theory. And what you can have as consequences of this, well, first of all, large language models are not a language theory, generative syntax is. If one claims that they are a language theory, people don't understand what the word theory means. And large language models are an experimental apparatus for the study of the theory of language, exactly like a particle accelerator is an experimental apparatus for the study of quantum field theory. And finally, as said, as a physicist, as a scientist, data and technology by themselves do not constitute science. What is the difference? Is that for us, I'm come back to what I said in the first lecture, that Galileo said that the universe is a book that is written in the language of mathematics, and the purpose of science is to obtain a concise conceptual explanation of natural phenomena. They should be testable and predictive, but the reason why it has to be predictive is because, you know, making prediction makes it falsifiable, and it allows you to discriminate between theoretical models. It's not the prediction is not the purpose of science. The prediction is how you check whether your science is right or not. The purpose of science is explanation, is essential explanation. Well, essential in the Ockham razor sense that ENSIA non sono moltiplicando per necessitatem, and, you know, parameters also non sono moltiplicando per necessitatem. And, you know, generative linguistics aims at producing such a theoretical model of the structure and functioning of language. And, you know, again, as a scientist, of course, some people now think that you can, you know, dispose of science because, you know, you have things that do predict, you know, correct predictions for you without the explanatory part. But I mean, the point is, if we renounce the explanatory capacity of theoretical science, we just give up our capacity to understand the universe as human beings. So I'm not, no, as a physicist, I'm not willing to give up the fact that the universe is knowable, that the universe is explainable. And, you know, I want to finish with, you know, what 1 century ago, you know, David Hilbert, you know, setting out this program for, you know, mathematics in the 20th century. And then what we were saying is that, well, that's what science works. We must know and we will know. And that is how science works. Okay, so I'm going to end here. And I just want to thank everybody for this lecture, and especially want to thank Noam and Bob for all of this. This is a picture that I took, you know, a long time ago when we had our first long Zoom discussion about a year ago that put all this work together. So yeah, thanks to both of them. Okay. Yeah, so there's a bunch of questions from the audience.
I think they can leave because we're officially done, but I think we have questions. And
yeah, there's a bunch of questions from the people on Zoom. If anybody else.
we also have questions and have a discussion.
Okay, so let me go to the. Okay, so questions from the audience. Kurush? I see you.
Hi. Hi, thank you. Now, when you were emphasizing this connection to perturbative quantum field theory, so the result that you have Feynman graphs and you have expansions and you compute up to certain orders, so it implies that there's a perturbative perspective on something that may have a non-perturbative formulation, which means non-perturbative quantum field theory. Now, in terms of language or linguistics, is there something somewhere that amounts to a non-perturbative way of thinking about?
I understand your question. It's a very interesting question. I don't know the answer. I mean, yeah, it's a very interesting question. If you want to think of these as being like the expansion in Feynman diagrams of your linguistic theory, is there something that's more like, I don't know, the kind of non-perturbative instant pulse or whatever? So I don't know that. It's a very good question. I'll try to.
May I ask one more question? In renormalization theory, or in this sort of concept of renormalization, there's the difference between renormalizability and the actual process of renormalization. I think it's the latter that you describe in terms of those Birkhoff type factorizations. But are there examples of linguistic theories that are not renormalizable? So in some sense, where you can show that your machine would not provide a sort of way of understanding through renormalization. Is there something like you cannot capture in terms of such binary trees? Sorry.
I understand what you're saying, but you see also in physics, you know, the difference between renormalizable and non-renormalizable is that, you know, in a sense, if you allow like for an infinite sequence of counter terms, everything is renormalizable, right? And so I don't know if if you can make that distinction in this setting. Also, well, to some extent, I'm only describing one theory, right? Because what I'm describing is this specific theory of pre-merge and from minimalist thesis. One would have to like compare it. This is also generally a question itself, like what variations on this theory one could consider that would alter some of the properties on the basis of which you could say, okay, this is preferable to some other theory. Like there are, for example, models where you have different forms of merge operations that are not these ones that I described here, and it's going to alter some of the, if you try to follow the same mechanism, it's going to alter some of the properties of your theory. And I don't know if some of these would give rise to something that maybe is the analog of a non-renormalizable theory in your sense, in the physics sense. I don't know. I mean, in some sense, this is doing the construction for one specific theory at this point. So yeah, I don't have like a space of theories in which to compare these properties.
Thanks.
Hi, Matilda. I'm sorry I can't be there, but hello from France. So I agree with your point that it's not surprising at all to find syntactic structure within a language model, simply because it, if it's going to be there, you should see it observed. But empirically, we often don't find that that's the case in language models. So there are many documented examples of so-called clever Hans effects, where something can demonstrate a syntactically valid behavior, but it turns out to do so based on an extremely shallow heuristic, which supposedly can do the thing, but is not related at all to the syntactic structure, especially in very controlled circumstances. And then even when you train on human linguistic data, you see this effect. So for example, if you train a language model on, say, a regular language like email addresses, it's very possible to extract the deterministic automaton from the state space, because it partitions the state space into the DFA. But then when you do that, you find that the DFA is totally awful. So the DFA does not give out the right regular language, even though the language model might be getting 100% on the performance on held out data. So I'm wondering what this perspective would say on the cases where you seem to see syntactic effects, but in fact, you're not getting anything really close to it at all.
No, that's right. I mean, this is actually also one of the reasons why I said, okay, in trying to study these correlations between specific this type of characters that I suggest that pair like one particular syntactic relations with the attention module probabilities, and see how they study how they correlate and where they maximize, right? Precisely because those will allow you to detect discrepancies between these things, where you maximize something, but it's actually going to be off where your actual syntactic relation is. And so that's right. You want some kind of quantitative way of making this distinction. Yeah, this is exactly what tell in cases like the ones that you're saying that you're off with respect to what these two things lie.
Yeah, okay, then I agree with that the theory steps in when the experimental data is ambiguous. Yeah, okay, great.
Hi, do you have the chance to answer another question?
Yeah, so what is the question?
Yeah. In order to really understand, I mean, I found everything you've done fascinating, and to really understand, I'd have to study the papers. So I don't want to claim I have a real understanding of what you've done. But I'm sort of curious about the relationship of this type of resultant theory to the place of language in mind, the theory of mind. Noam has always had a sort of a tension between two different approaches. Classically, it's been that language is a human activity and it's built into our biology, and that's why we have it. Lately, a little bit, he's tended toward a theory he would have at one time dismissed a lot. That's called the Platonic theory. There used to be people in linguistics who believed in it, like Paul Postal and the philosopher Jerry Katz. when no more has dismissed it, but he's considering the possibility that language is just this independent Platonic object. I'd like to cast this with an example, a linguistic example, to try and get us to think. There's a very nice paper by Danny Fox and Martin Hackle, in which they argue, surprisingly, but I think correctly, that all linguistic scales are dense. Okay. Now, in your view, in the view as I've understood it so far, if that were true, the most natural place to explain that would be in semantics, where you have topology, and you could make a special assumption about what the topology was like, and include density and some, et cetera, et cetera. And if that's so, that doesn't have to be true in general, right? I mean, you could have all sorts of topologies on your semantic space. You could include, non-dense scales. Of course, if you do, exclude non-dense scales, then you can't even put the natural numbers into language. But of course, there's good evidence that the natural numbers are not part of language. I think it would explain why the development is so slow and has to be taught. So the question is, how general is your theory? In a sense, does it go beyond human capacity? In which case we could ask, how does that relate to theories of physics, which I don't think mathematical theories of physics, as far as I know, I study physics some, I'm no physicist. Theories of physics don't try to explain all possible theories of physics. They try to explain the physics that we have. What's actually true. I don't think they claim that it's the only possible physical world. Of course, you could correct me. So if your question is meant to explain the kind of language what we actually have, that humans actually can have, then we have these kinds of questions, and we might need some more special assumptions. I'm not sure how that will. So it's a collection of questions. I hope it doesn't go too vague. Just curious how you think.
Yeah, no, let me say that, in some sense, part of what I've been, advocating in this lecture is the fact that, the mathematical formalism puts constraints for you. This is the same way that, like you're saying in physics, right? Physicists study, to some extent, they study possible theories, and where, the mathematics that governs the way these theories are organized are going to put constraints on them, and you expect that that's part of this whole idea, about the fact that things are knowable. You expect that your mathematical formula is putting enough constraints on your possible theories that will zoom in on something which is going to be the actual physics that we have, and that we can say that it has to be that way because the constraints force it to be that way. And so in some sense, this is the point of view that we're trying to advocate here, that the model of language that we're looking at has to be this way because it's in a similar way, very highly constrained by its own internal consistency, which can be described in mathematical terms as being consistency of the mathematics itself. And so some of the things that you empirically know are going to have to be there, to justify the way that language, human language actually works, in experimental verification, also have to be there for intrinsic structural reasons. So you want to come to a kind of picture that is sort of similar to what you have in physics, that on the other hand, your theory has to be consistent with the empirical results from experiments. It has to be falsifiable. It has to not contradict anything that is there for experimental necessity. But at the same time, is the way it is because of very strongly constrained mathematical formalism that force it to be that way. That's why, for example, symmetries are playing an enormous role in the development of modern physics, because they are an extremely constraining mechanism that tells you that certain physical models have to be a certain way rather than another way by structural necessity. So this is kind of the way when I see the interaction between trying to say language as it is in the human mind, as opposed to language as it is as a formal construction, as a kind of mathematical model. And we would like to come to the point where the constraint imposed by the mathematics reflects the necessities that one sees from the empirical side, just as one expects it to be in physics. I hope this answers at least in part your question.
Thank you.
Okay, more questions, anyone? Okay.
Thank you so much.
Thanks, Matilda.
Yeah, nice.